So we're going to conclude the simulation modeling video series with this last video on simulation with Analytics Solver Platform, or ASP. Analytics Solver Platform is a more appropriate tool for more complex simulations for several reasons. Firstly, it allows you to pick and choose from a variety of statistical distributions from the distribution menu without any need to code mathematical formulas into cells. Secondly, it allows us to quickly specify the output cell, and the actual simulation runs fast in the background without the need for cumbersome data tables. Finally, it provides all the stats and charts on the output distributions, like NPV in our example, one can possibly need, with the ability to analyze distributions with some simple visual tools, as you'll see shortly. Okay, so we want to demonstrate MPV simulation with an ASP or Analytics Solver Platform using the select2 MPV1 file. Make sure you open the one that ends with 1, which is the same file as before, but it's all of the manual simulation steps were removed, and it uses triangular rather than discrete distribution for the selling price. Okay. Then we're going to use the distribution button to set up all three of the distributions, and results output in cell to set up NPV as the output cell. So switch to the model. I'm going to zoom in so you guys can see this easily, and click on G5, our VC percentage cell, and then under Analytics Solver Platform Distribution tab, Common Distributions, I will open up the Uniform tab or Uniform Distribution, bring it into view, and I'll click on the lower button to select 65%, and then upper button to select 80%. And then you'll see the rectangular uniform distribution where every number between 65 and 80% is equally likely. When you save that, you'll see the PSI uniform shows up in the formula bar with both min and max cells and a base of 75. And then if I F9 this several times until I get a relatively high variable cost percentage, say 79, that will virtually guarantee me a negative net present value, right? But if I F9 it until I get relatively low variable cost percentage in the 60s, like 65, it can guarantee me relatively high MPV, regardless of what happens with selling price and demand further down the road. So then we go to the demand selling price distribution, rather, in cell C10. And under distribution tab, common triangular, we are going to use the minimum. For minimum, we're going to use 30 million. For most likely, we're going to use 35, and for maximum, we're going to use $50 million. And we'll show you this triangular distribution that is for some reason not showing. That's bizarre. Okay, it's not showing. It wasn't showing the numbers on a horizontal axis. Now it does. Here you can see this sort of triangle slanted towards the left. This representing actually a right skewed distribution because it sort of falls off to the right less sharply. And the most likely values are around 35 million, closer to 30 than 50. Okay, you can see that PSI triangular function inside as well. Then we switch to demand, which is a normal bell curve distribution with an average of 10 plus minus 1 units per year. Remember, these are aircraft, so that's why the number of units is relatively small, and each of them is priced relatively high, is in 36 million. So we click on cell D17 for the demand for year 1, and the distributions in common we pick normal. Once we bring that normal distribution in focus, we can set up the mean to be 10 units plus minus standard deviation of 1, and you can see how it's centered around 10, with 9 and 11 showing up quite a bit, 8 and 12 not as much, and very unlikely to see 7 or 13 units, with virtually impossible or no probability, no chance of getting as low as 6 or as high as 16. Now when I hit save, you'll notice I get the fractional number, so I need to round it by putting the round function around, no pun intended, right? PSI function, and then in the end type comma 0 close parentheses. But I also want to lock the reference to $I17 and $I18, because I want to copy this function to the right. So in order for you guys to see this, I'm going to make the D column really wide and click into it. Okay, so round, open parenthesis, matches up the close at the end. The entire PSI function is inside it. The 0 digits is the rounding, and then notice the dollar signs in front of I for both I-17 and I-18. Okay, so after I move this back and then copy this formula to the right and then readjust my borders, you'll notice that when I hit F9, all 6 of the input cells, variable cost percentage, selling price, and all 4 years worth of demand are all changing all at once. Okay, and then if I get a particularly high cost, about average, or I should say a most likely price, and then sort of average demand with some low years, some high years, I'm going to get a loss. Okay, I can probably get worse than that because we know the losses can be in excess of 50 million, but that's going to take a lot of hitting F9. It's not likely to happen. 14 million, 32 million, that's a big loss. High cost, below most likely selling price, relatively low demand except year 2, and so forth. On the other hand, if I F9 until I get a 3-digit gain, which I've seen like 101 here, right? Relatively low cost, relatively high price, and a decent demand. So you can see sort of these two contrasting scenarios. Okay, I'm going to zoom in, click on net present value, and designate it using analytical solar platform results output in cell as a result of the simulation output. Now I'm going to switch back to the presentation temporarily and discuss the options. The only option we care about is 5,000 simulation runs as recommended. 1,000 is default, 10,000 is the max. We want 5,000 in this class. The other 2 options listed here that have to do with how the random number streams are used across multiple simulation runs, whether they're the same or completely random every time you run, as well as these different types of samplings. None of this is really important for us at this sort of basic level. We'll leave all of those at their defaults except number of trials, which we want to make sure is 5,000. So before I run this, I want to show you the options button and just making sure that you have 5,000 simulation trials rather than 1,000. Okay, then what we're going to do, we're going to run the simulation by clicking on simulate button, and we're going to bring the output into view. Now you're probably going to have 2 of these vertical dash bars. Get rid of one by dragging it off the chart and position the other one so it's as close to 0. I have it here, the negative 5,000 as possible, and then you should get about 13, 14, 15% probability of loss. Then using the copy to clipboard, copy it and paste it someplace into the model. I'm going to then zoom in and not out so you can see the whole thing. So switching back to the presentation, we described that the resulting distribution is slightly right skewed with the average MPV about 50 million, which is almost dead on, 49,899. There's about 13% chance that the MPV will be negative. I already described that. And then we want to analyze a couple of ways of getting this risk down to less than a couple of percentage points. One is to increase, to rather cap the cost to 75%, or increase the average demand per year. Okay, so if I cap the cost to 75 and hit run, sometimes you have to hit it twice, you should get a relatively low, like 1% chance of loss. I'm not going to even save this, just going to keep the baseline scenarios, right? And then if I put this back to 80, okay, and then this to 12, and I run that, I should also get a relatively low loss, about 1.5% chance of loss. So you can see in both of these cases, I'm going to put this back to 10. I put the mean back to 10. In both of these cases, we were able to reduce the risk by either capping the cost or increasing the average demand. Okay, I'm going to save this, switch back to the presentation, and summarize. Okay, so this concludes the series of videos in the second part of the class that introduce the basic simulation concepts and emphasize the fact that simulation is an invaluable tool underpinning modern risk analysis. We described the simulation modeling process in some detail and demonstrated how to build simulation models for risk analysis with our MPV mini case. We did that both with basic Excel and analytical solver platform.